Hello, IB. We're heading into 21C and D actually in the same video, looking at the line of best fit. So we've been looking at sets of data over the last few days, and notice this data from the opening problem. We're talking about the age and then the distance that a discus is thrown, I believe, is what we're talking about here. So we've got a set of ages and a distance that each of these ages can actually throw the discus. And if we just wind up putting them on a scatter plot, we wind up getting the spread as it looks right here. I've also gone ahead and put all the data into our calculator, because what we'll want to do is if we open up a new page, calculator page, we'll want to actually run some statistics on, let's do our stat calculations, one variable, on the X and the Y. If we want to actually look at this data and try to figure out where is the average, or can I actually draw a trend line that will represent this data as shown here. So first thing we want to do is actually find the average of the age and also the average of the distance that's thrown, and that way we can have a mean point that we can then base our line on, because we want to have a line where about half the points are above it, half the points are below it, and it winds up representing our data really well. So let's go ahead and look at the average for our X, which winds up being, there we go, 15. And then if we run the same statistics for Y, we will wind up finding that our average is 19. So I'm going to bring that up a little bit. Or 29, excuse me. All right, so just looking at our age, yes, average looks to be about 15, distance thrown 29, that seems correct. If we plot that point, we wind up noticing that it is right here. So what we want to do is then base our, our trend line off of that mean point. So once I plot the point at 15 and 29, then I'm going to draw the rest of my line and have it pretty much go through the middle of all of my points as much as I can. So about half the points are above and about half the points are below. We've got a couple that are really close to it. Everybody's is going to look slightly different. This is not the most accurate way to do it when you guys are drawing by hand. We will use technology to draw in the future. But for right now, it's a good way to kind of just get a general idea of what your line's going to look like. So going back over those steps, anytime that you have a set of data with an X and a Y variable, we want to calculate the mean for the X values and the mean for the Y values. Plot your mean point on your scatter diagram, and then draw the line that fits the trend of your data the best that you can. All right, everybody's again will look a little bit different. So once we have that line, the most important part is then let's try to find an equation for it so that we can actually use it to possibly predict future values or some values that we didn't collect. So for example, if I have all these ages, I don't have a, let's see, I don't have a 17, well, I do have a 17-year-old. I don't have a 21-year-old or a, let's see, 15-year-old or 16-year-old. If there is any age that's missing, then I can wind up predicting based on this line how far they'll actually throw. So let's see what we can do with that. We know from year 10, year 9, year 8 that we need 2 points or a point and a gradient to wind up predicting our equation of a line, or to find the equation of a line. This mean point, though, wasn't originally part of our data. I could use it, though. It'll work great. Any point that's actually on the line, any 2 points that are on this line, we want to use. So, for example, these 2 points that I circled, they aren't exactly on the line, but I'm going to pick a point that's really, really close to the line as much as I can. So, again, we'll start with 2 points, because once I have 2 points, I can find the gradient. So if I look at this line, I'm going to use, let's say 12 and 20 is pretty close. And let's say I use, what's another one that's easy to count? I can use the 15 and 29, or I could use 18 and 39. I could even pick a point here or here. So it doesn't really matter. All of you guys might have just slightly different gradients, and that's because you chose just slightly different points. And we're approximating because we don't have a grid that's broken down. So we're kind of eyeballing where exactly these values are. So let's use, let's use 15 and 29, since we know that that point does hit exactly on the line because we made it. All right, so now we find our gradient. So y2 minus y1, so 29 minus 20. divided by x2 minus x1, 15 minus 12, and we wind up getting 9 over 3, winds up being a gradient of about 3, okay? Now, this might be close to what some of you guys get if you chose 2 different points. You might get 3.1, 3.2, 2.9, but it should be a gradient of approximately 3. So as we move from one point to the next, we're going about up 3 and to the right 1, up 3 to the right 1. Once we have your gradient, we also need a y-intercept. So we can either use our equation y equals mx plus b, and we can substitute in one of our points. So let's say we'll use 20 as our y, and our gradient is 3, our x value is 12, that corresponds with 20, and then plus b. So what we'll wind up getting here, 3 times 12, we get 36, plus b equals 20, so therefore b is going to be negative 16. So our equation of the line winds up being y equals 3x minus 16. Okay, so if this line continued, it looks like it would wind up dipping past 0, and it will hit the y-axis at negative 16. All right. Remember, you guys can also use your point and gradient equation as well. So I'll say or. You guys could use y minus your y value equals your gradient times x minus an x value that you want to use. So for example, this one, you might say y minus 20 equals your gradient of 3 times x minus 12. And I could either leave it like that, depending on what the directions say. If they don't specify, I could leave it like that. Otherwise, I can add the 20 to the right. I can expand the 3x minus 36 plus 20, and I wind up getting the same equation. All right, so just remember your options from the last couple years of math. Now that we have this equation, what we can do is actually do some interpolation. So interpolation coming from interpret the data. And we are using values that we're basically predicting data that's within the actual range that we're given. So if we look back at our graph, if we wanted to predict a value that's within this range, that would be interpolation. So how far will the average year 11 student throw? Well, we're looking at an age of 17, possibly. And we're using our equation of y equals 3x minus 16, was it? Yep. So what I could wind up doing is substituting our age, which is the x value for 17, minus 16. So therefore, we'll say that an average 17-year-old will throw about 35, and this was in meters. All right. Again, that's just predicting within the range that we're given. If we want to use our data or our trend line for extrapolation, which is outside of our data, the range that we're given, then that's kind of like a prediction. We don't know. We're only given values between 12 and, 12 and about 20 years of age. So if I wanted to predict how far a 22-year-old or a 30-year-old might throw, I could possibly use this line as well. Of course, there's going to be some error in this as well. If we go up to maybe a 50-year-old or a 60-year-old or a 70-year-old, we have to think again about what this trend line is really representing and if it's realistic. So how far could John throw if he was 22 years old? Then I'd wind up just substituting in 3 times 22. Oops. And then minus your 16. Similar. 50 years later, John is now retired after a successful career. Now he has time to throw a discus again. How far could he throw it? Again, if it's 50 years later, he's 72 years old. Can he really throw 219 meters? Is this line going to be realistic for every age? And that's something that we need to interpret when you guys are looking at your data, especially if you choose statistics for your project. Again, all these questions come up and we have to actually use our heads to analyze what we're actually finding here. So starting to get a little bit more accurate, as in 21C, when we are trying to find a line of best fit by hand and we're just using an average point and then we're kind of eyeballing the line. When we use least squares regression, we're actually going to start to use technology to force the line to be as accurate as possible. So we're looking at the squared distances or deviations, basically for each point away from whatever that middle line is. And if we take those square distances and we add them together, we really want those distances to be as small as possible. If we have the smallest possible distances away from the middle line, then that means our middle line is going to be very accurate. So when we do the least squares regression, technology is utilized because it can do that very quickly, very accurately, and it winds up being our best possible solution to use just because it's more accurate than by hand. Go ahead and pause so you guys can work through this on your calculator. So grab your calculator, go ahead and put in your data. So remember, we have to go to our lists and spreadsheets to put in our data. Enter it in. We need to label our X value and our Y value, or you could type in age and distance. Just to go back through the steps to make a scatter plot, if we wind up going to the next option for data and statistics, it just gives us a random display of points. However, there's no X or Y correlation yet. So you do have to click to add your Y variable and click to add your X. And that way it starts to show you what this, what your relationship actually looks like. So here are some new things that we can do with our calculator. Once you guys are here, we go to menu and we're going to analyze our data. You have the option of regression. And regression is winding up finding, kind of forcing a line or a pattern or some kind of equation to match our data. So you do not always have to go for a linear regression. You can see that there's a quadratic, cubic, quartic, all the different functions that we talked about earlier in chapters 5 and previously, that you can actually try to force to work if it looks like they're a better fit. But for us, we're going to stay with linear. And it automatically winds up giving you the line, which is what we were trying to estimate by hand. And it also gives you the equation. So if you notice, we're pretty close. The gradient should have been about 3.29, and then a negative 20 y-intercept. So we were relatively close, slightly off though. So again, the more accurately you choose your points, the closer that we're going to wind up getting to the actual gradient and the actual y-intercept. Few other items of interest possibly is when you analyze your graph, you can also show residuals. So you can hide residuals or you can show them, but if you wind up showing them, you can tell what your sum of all the squares is. So it'll tell you sum of squares was 232. So again, if you're doing any kind of analyzing in the future, another option for you guys to take a look at, nothing that we'll need at the moment. And last but not least, I'm going to open up a calculator page and just take a look at our menu. Looking at statistics and stat calculations. Instead of going into one variable statistics, which is what we've been using recently, if we go to linear regression and we type in the X and the Y sets of data that we were using, it'll give you it'll also give you the equation. So it'll give you your gradient, 3.29, it'll give you your y-intercept at negative 20, and then also gives you your r squared and your r values. So if you notice your r value, our r value is the value that winds up telling you how closely the calculator was able to make your line of best fit your data. So r value that's very close to 1 winds up being a very, very, very accurate line. So 0.9 is very close to basically a great representation of what your line is. And then your r squared is 0.8. So just notice for linear equations, if your r is negative, that means it's a very strong negative gradient. If it's positive, then it's a very strong positive gradient. Once you guys have found your equation and your r value, so your r value is support that your equation is relatively accurate, then you can continue and wind up analyzing data and doing anything else, predicting, extrapolating, interpolating, whatever you guys need to do. Last thing to consider is that if you do wind up getting an R value that's between negative 0.5 and 0.5, which is very moderate to weak correlation, you wind up, or anything that's less than that, is it worth you know, actually using a linear equation to represent your data. So these are some things that you guys are going to need to analyze when you actually look at the data. Does it make sense? Is there a different fit that would be better besides linear? And is it a strong enough correlation for me to actually even make a prediction based on the equation that I found? So again, anything that's less than 0.5 or greater than negative 0.5, so in that interval, where it's not exactly the strongest line. 0.9 is extremely strong, which is what we found, and you guys know what that looks like based off of our scatter plot, but anything that's between that window might not be the best way to go. All right, guys, that's it for 21C and D. We'll see you guys in class. Have a great night.